In functional analysis, linear operators do not act in isolation. Every operator T is paired with a secondary mapping, a companion that dictates how the transformation interacts with the functionals measuring its output. In his foundational texts on functional analysis, Charles Hermite provided the rigorous derivation for this relationship, known as the adjoint. We start with a bounded linear operator, T. It serves a specific function, taking vectors from an input space, x, and mapping forward into a target space, y. Alongside these primary spaces sit their dual spaces, denoted x' and y'. These are the spaces of all bounded linear functionals, the tools used to measure vectors and assign them scalar values. If our operator T forms a bridge moving forward from x to y, we must define the mechanism that connects their dual spaces, moving backwards, from y' to x'. We will construct the Banach adjoint operator, prove that it preserves the original operator's norm, and trace the technical pathway that distinguishes it from the Hilbert adjoint. Formalizing this backward mapping is the necessary step for extending finite-dimensional linear algebra into the general framework of operator theory. A vector x in x maps to tx in y. We apply a functional g from y' to measure tx, yielding a scalar. This directly assigns input x a scalar, creating functional f. The adjoint operator, t cross, transforms output g into input f. This gives our formal definition. T cross applied to g, evaluated at x, is identically g evaluated at tx. It is important to distinguish this from an inverse operator. An inverse, t inverse, would map vectors from y back to x. The adjoint t cross operates on a different level. Its domain is the dual of the target space, mapping exclusively between spaces of functionals. Consequentially, the choice of how we measure the output determines how the input is perceived through the transformation. In finite dimensions, operator T is represented by matrix TE, acting on vector x. Functional G is a row vector. Using associativity, we multiply G by TE first, producing our pulled-back functional F. Applying the transpose writes F as a standard column vector. The matrix transpose is the explicit representation of the adjoint operator within finite-dimensional spaces. Kreyszig's theorem 4.52 proves that the adjoint operator is norm-preserving. The norm of T cross is exactly equal to the norm of the original operator T. Through standard algebraic bounding, it is straightforward to show the adjoint cannot exceed the original. The proof requires demonstrating that it cannot be smaller either, capturing the full transformation magnitude. This is where we employ the Hahn-Banach theorem. For any output vector tx0, Hahn-Banach guarantees the existence of a functional, g0, that measures its length without any loss of value. Because this functional exists, the measured value reaches the full magnitude of the output, forcing the norm of the adjoint to equal the original. This ensures that the dual space serves as an isometric reflection of the original space. While the Banach adjoint T cross and the Hilbert adjoint T star share a common origin, they are mathematically distinct. A diagram shows operator T mapping between Hilbert spaces H1 and H2. The Banach adjoint maps backwards across their duals. Rie's representation provides vertical bridges connecting these layers. The Hilbert adjoint T star is the full composite path, descending, crossing, and ascending back to H1. Because these vertical bridges involve complex conjugation, the Hilbert adjoint is conjugate linear. Conversely, the Banach adjoint remains strictly linear, as it never leaves the space of functionals to cross those bridges. The Hilbert adjoint is a highly specific geometric construction used to keep the adjoint operation entirely contained within the original vector space. This specific Hilbert structure was essential to Erwin Schrödinger's wave mechanics. In quantum theory, adjoints are necessary for defining operators that represent observable physical values. While T star is the standard in physics, T cross is the broader topological definition. The Banach adjoint is a norm-preserving representation of an operator that allows us to analyze transformations within the dual space. In fields like optimization and differential equations, this allows for the construction of solutions that may not be directly accessible in the primary space. For those studying the works of Charles Hermite or the foundations of operator theory, this duality is a central component of the curriculum. Mention in the comments which theorem from functional analysis you would like to see derived next. The existence of the adjoint confirms that every linear transformation carries an inherent structured relationship with its dual.